Sketch the graph of the function f of x equals x times the square root of 2x plus 12 by determining the parts a through I. F of x equals x, a polynomial term, the domain will be all real numbers, times the square root, an even root, of 2x plus 12. We can rewrite the square root as a fractional exponent. It will be 2x plus 12 to the first power second root, or 1/2 power. The denominator of a fractional exponent is the root. It's an even number here, and the domain of an even root is not necessarily all real numbers. The domain requires that what is inside of an even root has to stay greater than or equal to 0. So 2x plus 12 has to stay greater than or equal to 0 for the domain here. We can solve for x by subtracting 12 from both sides and dividing both sides by a 2. And the requirement for the domain is x has to stay greater than or equal to -6. So for part A, the domain will start at -6. It will include its square bracket and everything greater than or equal to that, so it'll go to positive infinity. For part B, we want to determine whether there is any symmetry. This is done by evaluating f of -x and comparing it to the original function f of x. F of x inside of the root is made up of an odd power. This is an implied first power on the x, which will have origin or odd symmetry, added with a constant. And a constant always has y-axis or even symmetry. Since the two do not match and they're added together, f of x will have no symmetry. F of -x is -x times the square root of 2 times -x plus 12, which is -x times the square root of 2 times -x is -2x, and then plus 12. Comparing this result to the original, it does not equal the original, because inside the root there's a -2x but a positive 12 still. And since it does not equal the original function f of x, it will not have y-axis or even symmetry. And comparing it to the original, there is a negative out front, so it looks like it might have a chance of being negative of the original, but once again, inside of the root, the 2x term has the opposite sign, while the 12 term has the same sign. And so this also does not equal the negative of f of x, and it will not have origin or odd symmetry either. So for symmetry, it has none. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. The corresponding y-coordinate can be found by plugging the x-coordinate back into the original function, y equals f of 0, which will be 0 times the square root of 2 times 0 plus 12. 2 times 0 is 0, plus 12 is 12. So you have 0 times the square root of 12. 0 times anything is 0. We had an x-coordinate of 0. We found a corresponding y-coordinate also 0. So 0, 0, the origin is the y-intercept. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, can be set to be 0, and we want to solve for all x's. It's best to have the function fully factored for this, so inside of the square root we can factor a 2 out. It will not come outside of the square root because 2 is not a perfect square, but it will leave behind an x plus 6. The x factor would give us x equals 0. The x plus 6 factor, even though it's under a square root, will still give x equals -6. because we need it to be 0 for the square root to be equal to 0. We have a y-coordinate of 0. These are the corresponding x-coordinates. So this will give 0, 0, and negative 6, 0. For part E, we want to determine if there are any vertical asymptotes. F of x is x times a root of a polynomial. It's all in the numerator. There is no denominator, so there will be none. For part F, we want to determine if there are any holes in the graph. F of x has no denominator, so there will be none. For part G, we want to determine the end behavior, horizontal asymptotes or slant asymptotes. F of x is a polynomial term multiplying a root, a fractional exponent that's a positive exponent. There's no denominator, so there will be no horizontal asymptotes or slant asymptotes. But it will have left end and right end behaviors. Looking at the domain, the left end is an included finite value of negative 6. And that means it'll have a left end point. So for the left end, there will be an end point that has an x-coordinate of negative 6 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of negative 6, which is negative 6 times the square root of 2 times negative 6 plus 12, which is negative 6 times the square root of negative 12 plus 12, which is negative 6 times the square root of negative 12 plus 12 is 0. The square root of 0 is 0 times the negative 6 will be 0. So we have a corresponding y-coordinate of 0. So there's the left endpoint. Back up here for the domain, the right end is positive infinity. So the right end behavior can be determined by the limit as x approaches positive infinity of the function x times the square root of 2x plus 12. Inside of the square root, only the highest power term will matter. 2 times positive infinity will be positive infinity. The root of positive infinity is positive infinity, and then times a positive infinity will still be positive infinity. So the right end behavior will be positive infinity. We'll be sure that it follows these end behaviors. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. We'll take the first derivative from the original function f of x. It's best to use the fractional exponent version, this one here. F of x is a product of x times 2x plus 12 to the 1/2. We will have to make use of the product rule, which will take some room. So this can be worked out on another page. F of x equals x times 2x plus 12 to the 1/2 power. The first derivative will be a product rule. Derivative of the first, which is a 1, times the second left alone, 2x plus 12 to the 1/2 power, plus the first left alone, x, times the derivative of the second, which is a power rule. Bring the power down, 1/2. Leave the inside alone, 2x plus 12. Subtract 1 from the power, I will call that 2/2, and then multiply by the derivative of the inside to complete the chain rule. The first term is 1 times an expression. 1 times anything is that same thing, so that'll be 2x plus 12 to the 1/2 power. The second term We can put the constants together. There's a 1/2 and a 2. 1/2 times 2, we can multiply the numerators. 1 times 2 is 2 over 2. 2 over 2 is a 1. So we have a positive 1. There is an x. And then there is a 2x plus 12 to the 1 minus 2 negative 1/2 power. We want to fully factor the first derivative. There is a common factor of a power of 2x plus 12. We can factor out the lower of the two powers. That'll be the negative 1/2. It's lower by being negative. So we can factor out 2x plus 12 to the negative 1/2 power. Factoring is division, and division is subtraction of exponents. So by factoring out 2x plus 12 to the negative 1/2, we will be subtracting a negative 1/2, which is equivalent to adding a 1/2 to each of the powers. Adding a 1/2 to this, 1/2 plus 1/2 is 2/2, or 1. And we will get 2x plus 12 to the power of 1, which is just 2x plus 12. Adding a 1/2 to this, negative 1/2 plus 1/2 is 0. And anything raised to the 0 is a 1. So we will have x times 1, or just x. So we have 2x plus 12 plus x left over after factoring. So it'll be a 2x plus 12 plus x. So we have a 2x plus 12 to the negative 1/2 power. In the square brackets, we can combine like terms together. I'm going to turn it into parentheses now. 2x plus x is 3x. And there is a plus 12. We want all powers in the first derivative to be positive, so we will move the 2x plus 12 to the negative 1/2 to the denominator. The 3x plus 12 will stay in the numerator. And we will have a 2x plus 12 in the denominator as a positive 1/2 power. Positive 1/2 can also be written as square root, so we can write it as the square root of 2x plus 12. And we will want to fully factor the first derivative. In the numerator, there's a common factor of 3. Factoring that out will leave an x plus 4. And in the denominator, inside of the root, there is a common factor of a 2. It's not a perfect square, so it'll stay inside of the root, but it'll leave behind an x plus 6. We now have the first derivative written as a single fraction. All powers are positive, and it is fully factored. This is the version we're going to want. So here we found it to be a 3 times x plus 4 divided by a square root of 2 times x plus 6. Now that we have it written as a single fraction, all powers are positive, and it is fully factored, we can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, the x plus 4 factor tells us that x equals negative 4. From the denominator, the x plus 6 factor tells us that x equals negative 6. We will now check to see which of these are in the domain. The domain is all real numbers greater than or equal to negative 6. It does include negative 6. So x equals negative 4 is greater than negative 6. It's in the domain, and it is therefore a critical number. X equals negative 6 is the left endpoint. It is included. It's in the domain. It's also a critical number. We can now draw a domain line, a line representing the domain. It has a left end of negative 6. It has no right end because it goes to positive infinity. The left end is included by square bracket. However, x equals negative 6 was found to be a critical number, and it is removed, and therefore it will be a round bracket at negative 6. And we can put any other critical numbers on here. There's a -4, which will go here. This splits the domain interval into two separate intervals. We can pick a test value in each of the intervals. The first interval, -6 to -4, we can pick -5. The second interval, -4 to positive infinity, we can pick 0. We can now test the trend by plugging the test values into the first derivative. We only care whether it is positive or negative, so the best place to plug in is the fully factored version, which is this one here. A couple things about this. First of all, in the denominator, what's inside of the square root is guaranteed it will stay positive. That's a requirement for the domain. The domain says that x value has to stay greater than or equal to -6, and -6 isn't included here, so we will be greater than -6, and anything greater than -6 added to 6 will be a positive number. So that square root in the denominator is all positive. Also in the numerator, the 3 is positive, and therefore neither of those will determine whether the first derivative is positive or negative. It depends only on x plus 4. Plugging in the test value of -5 plus 4 is a negative. We have a negative first derivative. This corresponds to a decreasing trend. Plugging in 0 to the portion of the first derivative that matters, 0 plus 4 is positive. We have a positive first derivative. This corresponds to an increasing trend. Right at the critical number of x equals -4, we have a trend change from decreasing to increasing, so x equals -4 will be a relative minimum. It has an x-coordinate of -4 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of -4, which will be -4 times the square root of 2 times -4 plus 12, which is -4 times the square root of -8 plus 12, which is -4 times the square root of 4. And the square root of 4 is a 2, so -4 times 2, which is a -8. We have a corresponding y-coordinate of -8. Now, at the left endpoint, we also had a critical number of x equals -6, so this is a critical number here. It's the left endpoint of the domain, and it has no trend to the left of it because the graph doesn't exist over there, but to the right of it, it does have trend of decreasing. And therefore, at x equals -6, we will have a relative maximum. X equals -6, notice, came from the denominator, so it isn't a normal maximum, it's a cusp maximum. So we have a cusp maximum and an x-coordinate of -6 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of -6, which is -6 times the square root of 2 times -6 plus 12, which is -6 times the square root of 2 times -6 is -12 plus 12, which is -6 times the square root of -12 plus 12 is 0. Square root of 0 is 0 times -6 will be a 0. We have a corresponding y-coordinate of 0. -6, 0 we've seen already. It's actually the left endpoint, and it's one of the x-intercepts up there as well. For part I, we want to determine the intervals of concavity and any inflection points. This will involve the second derivative, f double prime of x. We'll take it from the first derivative. We don't want to take it from the fully factored and written as a single fraction version of it. It's messier to work it out from there. We'll take it from a different version, but it'll also require some room, so we'll go back to this other page. The best place to take the second derivative from will be this one here. It will be a product rule still, but it's better than having it written like so, because that will require a quotient rule and it'll be quite messy from there. So we'll take the second derivative from this version here. The derivative of the first, which is a power rule, bring the power down. Leave the inside alone. Subtract 1 from the power. I will call that 2 halves. Multiply by the derivative of the inside to complete the chain rule. And then times the second left alone. Plus the first left alone. Times the derivative of the second, which will be a 3. For the first term, we can multiply the constants together. We have a negative 1/2 and a 2. Negative 1 times 2 is negative 2 over 2, which is negative 1. So we'll have a negative 1. The 1 is implied. We will have a 2x plus 12 to the minus 1 minus 2 minus 3 halves power, and then times a 3x plus 12. For the second term, we can move the 3 to the front, and we have a 2x plus 12 to the negative 1/2 power. We want to fully factor the second derivative. There is a common factor of a power of 2x plus 12. We can factor out the lower power of the 2, and that'll be negative 3 halves. It's lower by being more negative. So we can factor out a 2x plus 12 to the negative 3 halves power. Factoring is division. Division is subtraction of exponents. By factoring out 2x plus 12 to the negative 3 halves power, we will be subtracting a negative 3 halves, which is equivalent to adding a 3 halves to each of the powers. Adding a 3 halves to this power, negative 3 halves plus 3 halves, is a 0. And anything raised to 0 is a 1. So all of that will be a 1 times the negative, so negative 1, and then times the 3x plus 12. Adding a 3 halves to this power, negative 1/2 plus 3 halves is 2 halves, or 1. It'll become a power of 1, and so it'll be 3 times 2x plus 12 to the first power, or just 3 times 2x plus 12. There's what's left over. So we will have a negative times the 3x plus 12. And we will have a positive 3 times 2x plus 12. So we have a 2x plus 12 to the negative 3 halves power. Inside the square brackets, we can distribute the negative in here, which will be minus 3x minus 12. We can distribute the positive 3 in here, which will be plus 6x plus 36. So we have 2x plus 12 to the negative 3/2 power. We can combine like terms together inside of the square brackets. I'll write it as parentheses now. A negative 3x plus a 6x will be a 3x. A negative 12 plus a 36 will be a positive 24. We want all powers to be positive, so we'll move the 2x plus 12 to the negative 3/2 to the denominator. The 3x plus 24 can stay in the numerator. The 2x plus 12 will move to the denominator to become a positive 3/2 power. We want to fully factor the second derivative. In the numerator, there is a common factor of 3. Factoring that out will leave behind an x plus 8. In the denominator, there is a common factor of 2, though it's not a perfect square, so it cannot come outside of the 3/2 power, which means third power but square root. Factoring out the 2 will leave behind an x plus 6. So we have the second derivative written as a single fraction. All powers are positive. It's fully factored. There's the version we're going to want. So it was 3 times x plus 8 divided by 2 times x plus 6, and then that entire quantity to the 3/2 power. Now that we have the second derivative written as a single fraction, all powers are positive, it's fully factored, we can set the numerator equal to 0. We can set the denominator equal to 0 and solve for all x's. From the numerator, because of the x plus 8 factor, we get x equals negative 8. From the denominator, because of the x plus 6 factor, we get x equals negative 6. We'll now check to see which of these are in the domain. The domain is all real numbers greater than or equal to negative 6. Negative 8 is not greater than or equal to negative 6, so this is not in the domain and will not be a candidate number. X equals negative 6 is in the domain by being the left endpoint, so it is a candidate number. We can now draw a domain line. It has a left end of negative 6, but no right end. The left end of negative 6 is included, but we found x equals negative 6 to be a candidate number, so it will be removed and there will be a round bracket for negative 6. We put any other candidate numbers on here. There are no other candidate numbers. Therefore, we have only one interval to test on. It's the entire domain interval. Apparently, the concavity will be the same through the entire domain. We can pick a test value somewhere between negative 6 and positive infinity. 0 will work. And we can test the concavity by plugging the test value back into the second derivative. We only care whether it's positive or negative here. The fully factored version is a good version to plug into. In the numerator, 0 plus 8 is positive, times 3 is positive. In the denominator, 0 plus 6 is positive, times 2 is positive, and then to the 3/2 is positive. That denominator is guaranteed positive once again because that x plus 6 will stay positive for the entire domain, other than negative 6 itself, which is not included. So we have a positive over a positive, which is a positive second derivative, which corresponds to concave up. It will be concave up over the entire domain. Since the concavity never changed, there are no inflection points. We can now draw the graph. We have a vertical axis. We have a horizontal axis. we have the domain starting at -6, and we found the left endpoint to be -6, 0, which is also one of the x-intercepts. So we can put that on the graph and label it. We have no symmetry. We have a y-intercept of the origin, and that will also be one of the x-intercepts because it's crossing both axes. So it's going to cross here the origin. We can label that. It has no vertical asymptotes, no holes. We've accounted for the left endpoint. The right end will have behavior of positive infinity. That means it'll head up here for the right end somewhere. We'll be sure that it does that. Right at the endpoint of -6, 0, we found it to be a relative cusp maximum. It's only a half cusp because it's a left endpoint and we'll have no graph to the left of it, only to the right of it. So it'll have a half cusp shape. A cusp max normally looks something like this, but it will only have the right portion of that. It has a vertical tangent line happening there, so it's straight up when it comes off of it at first. So I have a shape something like that. At the point -4, -8, we have a relative min. It's a normal relative min. So that'll be down here somewhere. We can label this -4, -8, and give it a relative min shape to it. We found no inflection points, but we do see that it should remain concave up the entire time, so it should stay curving up the entire time. We'll be sure that it follows that. So now we can connect these pieces together. So here it connects together. Notice it's remaining concave up. It's curving upward. It's decreasing in that range. Yeah, decreasing and concave up. And then it becomes increasing and concave up for the portion over here. So it'll be curving upward, continuing to curve upward, like so. It does have the right end behavior of positive infinity as it should. And it's following the domain starting at -6, including it. It's a left end point. We found it to be a cusp maximum with a right cusp happening. Everything's being followed here. Therefore, this will be the graph of f of x.